Welcome to today's Europa Village session. Today we will meet five new projects: CYBELE, the European Processor Initiative, Evolve, Hidalgo, and PRACE. So first of all, let me introduce myself. I am Pascal Bernier-Bruno. I'm the Communication Manager at ETP4HPC. The European Technology Platform for HPC is a non-profit association that promotes European HPC research. Now, our association has more than 100 members from industry and academia. Nearly 40% of our members are SMEs, but we also have all the large vendors and large HPC centers. And we are a private member of the Euro HPC JU, where we have an advisory role. So concretely, what we do is that we propose research priorities in the area of HPC technology, and this is used by the Euro HPC to define the contents of their funding programs. So it's very gratifying for us to see the actual funded projects come to life and produce results in the domains that we recommended for funding. And if you want to know more about us, we have a virtual booth here at the Teratec Forum, so please visit us. Now, a couple of practical information because we get really into today's topics. We want this to be an interactive session. It's fully live, as you may have noticed. So you can ask your questions at any time in the question panel, and we will answer them after each project presentation. And also an important point, this session is recorded, and the recording and the slides will be available on the Teratec Forum website. I don't know exactly when, but they will definitely be available. So let's get to today's agenda. So today we will meet CYBELE, presented by Sophie Guégan-Marat from Atos in France. And then we will have the European Processor Initiative, represented by Fabrizio Maguliani from E4 in Italy. And then we'll have the Evolve project, represented by Jean-Thomas Acquaviva from DDN in France. And then we'll have the Hidalgo COE, presented by Javi Nieto from Atos in Spain. And we will finish with PRACE, represented by Joost van de Vondel from CSCS in Switzerland. So I'm done. Now it's time for the speakers. So Sophie, are you ready to share?
Yes. Just let me share my screen.
And I will go invisible, but I'm still here. So we can see your slides, but very small. You're not in slideshow mode.
Better?
Yeah, that's perfect.
Okay. So good morning, everybody. My name is Sophie Guégan-Marat, and I will present you the CYBELE project. So first, a context. If we are following the same path that we are on, the food waste and loss will continue to increase and increase by the years to come. But the UN has set a target to cut in half the food waste and the food loss by 2030. So this is a really ambitious target, and a huge effort should be made to reach that target. So that's where the CYBELE project is born. It's a European project. And the goal is to use machine learning and high performance computing applied to agriculture. So it's including Atos. It's a 3 years project, and it's 12 million euros of funding. And as we will see later on, there is 9 demonstrators involved in the CYBELE project. So the goal is to have a new way for precision agriculture and precision livestock farming. We want to use all the data that are available, either weather, soil temperature, sea condition, UV factors, that can be given by a local sensor in the field, implemented in a farm, or sensor or information coming from satellite data, and use that to make more informed decision. So for example, classification of crop quality, if we need to fertilize some plants to monitor pig weight and health, and so on. And from all those informed decisions, we will have better food quality, longer shelf life, higher yield. We can reach also a new market, and the most important, we will have less food waste. So for this purpose, we will use HPC abstraction. So we will give HPC capabilities to people without having the need to be a HPC expert. So HPC will be more accessible and having faster time to market for the solutions. Concerning artificial intelligence and machine learning, everything obviously will be faster using HPC. So the model will be faster to build, to train, to modify, and so on, given the computing power. Also have intelligent query building, so search for insight in complex data and exposing previous hidden meaning. This can be expressed in form of a dashboard for the farmers or for the fishermen to get information without still having the knowledge of HPC infrastructure. So a little bit about the 9 demonstrators that were involved in the CYBELE project. So the first one is about organic soya yield. So to increase both the quantity and the quality of the soya production that will be mainly used for farming, for animal livestock. The demo 2 is about food safety. So to assess the risk management and also to predict food recall as earlier as possible, for example, even before it leaves the factory. Demo 3 is about predicting the extreme weather events that can happen, like hail or frost, that are really damaging for the harvest, and also to model the phenology cycle. Demo 4 is about autonomous robotic system, like to gain access to soil assessment, crop assessment, harvest assessment, so to have a really precise information about the growth of the crops. Demo 5 is about monitoring crop yield and at a bigger scale monitoring agriculture. Demo 6 is about using images to be able to know the weight of the pig and their behavior. So this way, just by taking a picture of the pig, you will know when it's time for them to go to the slaughterhouse. Demo 7 is to improve the health and the health care of the pig, and also the production and increase the meat quality. Demo 8 is about having a sustainable exploitation of fish and to prevent overfishing. And Demo 9 is to maximize the conversion rate, so the food added to the biomass of fish and how it will impact the growth of fish. We will look a little bit deeper on the which tools was involved. So this demonstrator is composed of 3 subcases. The first one is the spatiotemporal forecasting of fish abundance using environmental data, satellite images, and coming from all the fleet vessel, we will be able to improve the data and tool and to predict where the fishes are in a part of the sea. The subcase 2 is to optimize the database system on board of a specific vessel.
I go on, Pascal?
Yeah, you go on, and we'll have Sophie at the end. Okay?
Okay.
So 12 minutes.
Yeah. Give me 1 second to switch all
Yeah,
to
your
stuff.
your 12 minutes will start when you're ready. Don't worry.
Share my screen. This one, share. Do you see my screen
Yes,
now?
perfect.
Okay, so thanks everybody, and thanks Pascal for giving us the opportunity to talk about the European Processor Initiative. The European Processor Initiative has been funded within the European Horizon 2020 Research and Innovation Program under Grant Agreement number 826647. Now, give me a couple of seconds to talk about the general overview and what are the components of the European Processor Initiative. My name is Fabrizio Magogliani. I work for E4 Computer Engineering, and I'm presenting this chat about the EPI on behalf of the whole awesome team of EPI. The story started in March 2017 when the European Commission launched the EuroHPC declaration for getting Europe self-sustainable and autonomous in terms of technology. In November 2018, the EuroHPC joint undertaking funded by 1 billion euro was started among European countries and institutions to develop a world-class supercomputing ecosystem. And on October 2020, we have 32 countries participating in the EuroHPC and counting. What are the ambition of Europe in EuroHPC? Basically, is developing a native European supercomputing ecosystem. And when I say ecosystem, I mean the full spectrum of technologies, so hardware, software, networking, and applications, and accessing this technology through the cloud, and also fostering the European SMEs, private users, to use high-speed technologies and high HPC technologies for getting more and more competitive in the very challenging industrial market. Last but not least, is the objective was to stimulate a native European supply chain for these technologies. The European Processor Initiative, as of now, has 28 partners in 10 European countries, and you can see in these slides the members. Basically, almost all the European countries are covered, and there is a very good mix among large industries, SMIs, university centers, and compute centers. We are covering, the API initiative is covering the full spectrum of users, suppliers, developers, and applications. The objectives, as I mentioned before, is to develop a EU-designed high-end microprocessors, mostly for supercomputing and edge HPC segments, and doing that via a complete, sustainable, and competitive companies and ecosystem. Europe needs to develop a sovereignty and not being at the threat of any embargo of shortage of components by non-European countries. and also has to cover the full technological TRL, technical readiness levels, and deliver a fully working components and system. The key, the core of the EPI is the common platform, where inside a single common platform, there will be the integration of customized function chips in package on board level over PCIe or network link. You can see the picture. The EPI common platform design is basically the glue within which the different components are going to be integrated and made available. Of course, this is a conceptual layout. The real layout is in design, is in development, with some parts already taped out. And I think that you all have been reading the press release about the tape out of the test chip, which is going to be part of this picture. Be aware that the common platform will be designed for the best byte to flop ratio. That's because of its mainly focus towards HPC applications. It will have HBM2E, DDR5 and PCIe Gen 5 connections, and it will have a coherent NOC at system level cache to keep data as much as possible local. A die-to-die interface, the open to other vendors and to EPI components, is also available through this common platform. The computing units are based on ARM with the SVE extensions. It is also complemented by MPA and PPA, multipurpose processing array, and the RISC-V based accelerator, which is going to be called EPAC, European Processor Accelerator, and also by an embedded FPGA for specific applications and for specific usage. The objective is to develop also a complete set of software ecosystem, including the Linux operating system and low-level software security and power management, where the focus is to make sure that this system will be usable in a very frugal power envelope, as well as with the maximum security feature to enable industries, companies, SMEs, and other components to safely run their application on the system without any problem of losing data. And on top of it, having programming tools and libraries and other components mandatory for developing the applications and to optimize the applications for this platform. Also, automotive members are in the project, and they will use the common platform design to develop automotive-specific applications and components for their own objectives. Of course, the methodology that has been used for developing the processors and the other components is co-design. That's because we firmly believe that it is absolutely necessary to put around the same virtual table in these days the application experts, the guys who will run and develop the applications, with the hardware architects and with the model and simulation of the common design. during the development of the processor, there has been an extensive set of application runs to model the hardware components, and we are in this moment developing models for the performance and the data transfer of the processors on some selected applications. This is a very preliminary functional picture of the EPAC test chip, the European Processor Initiative Accelerator test chip. The test chip is a precursor of the accelerator and has been developed for testing specific features and the integration of different components, as you may see in this picture. The test chip has been taped out 2 or 3 weeks ago, and we are waiting in the next week the first samples of the test chip to return from the foundry, and we will furiously put it at work. The common platform has, of course, the objective to harmonize in a single design the different computing components, as you may see in the slides, and to make sure that there will be a harmonized set of features provided by the common platform. Am I running late?
1 minute to go.
Okay, thanks. I'm close to finish. To make sure that everything will be harmonized, there won't be any specific component taking any undue advantage against the other components, and all of these components will be harmonized with the software components. Be aware that EPI is not only hardware, is not only a processor, but is a complete ecosystem ready to use for the normal users. And the major and the co-design is being applied as the development methodology. The software development vehicle has been developed to run the benchmark on top of Linux, and it is currently used as a development suite for the processor and the accelerator. The roadmap, and I'm going fast to meet the deadline.
Yeah, and you have questions.
Yes,
So.
yes. The roadmap that we can envision as of now is having the first generation called RIA available in 2022, and then the second generation family is called Chronos, is planned for 23-24, and then the future will provide us with the direction where to go. The conclusion, we have right now in place a truly European effort to make available a leading edge technology for supporting the European companies in being competitive at the worldwide level, and we want to make sure that the processor is suitable for several different markets with a focus on HPC. With this, I thank you, and I return the control to Pascal.
Yeah, so we have some questions from the audience. So actually, I had a question about what happens next, but I see our audience is wondering too. So there is a question from Henry Strauss at SICOS. First of all, how can you think that 1 billion euro is enough for the goals you have?
We are not sure. But all the companies member of EPI have a vision, and this vision is that the European Union has to support our effort, but each company has to put its own money and its own brains to this initiative. Therefore, the 1 million is going to be complemented by in-kind or in real stuff effort by the single companies. I'm not focusing mostly on the 1 billion. I'm focusing about the vision to make Europe self-sustainable, master of its destiny, if you understand what I mean, Henry.
Okay. And another question from Henry is, have you decided yet for the manufacturing partner?
We have decided. We have a number of options about who is the manufacturing partner of the processor. We are in this moment not at liberty to mention the name because of still ongoing negotiation with these partners, but we have a clear vision of who it may be.
Okay, and one last question from Ravi. Which tools are available for doing some test porting codes?
Thanks a lot, Javi, for asking. At the end of EPI 1, which is going to be November 30th, 2021, we hope that we are working in order to have EPI number 2 starting, and EPI number 2 will make available some samples or some development platform to the general users to get access, preliminary access to the RIA processor. So stay tuned. At the end of the process, we will make known the rules for granting access to EPI number 2 and the development platform. I see that Pascal is just killing me with her eyes.
No. You're perfect. You're exactly on time. So it's just so now. Thank you for those questions. I hope we answered the questions the way you. I hope we correctly answered your questions. And it's time to go to the next speaker. You can continue the conversation offline, of course, in the chat or in the Teratec Forum platform. And our next speaker is Jean-Thomas. Jean-Thomas, are you ready? Thank you very much, Fabrizio. Thank you.
You're welcome, Pascal.
And good luck for the next project.
We will make it work, Pascal. With the help of everybody, we will make it work. I keep my mouth shut now.
Okay. Thank you very much. So I will stop sharing. Jean-Thomas, can you share your screen? So Jean-Thomas is presenting Evolve.
I'm trying.
Yeah, it's not in slideshow mode yet, but...
Is it okay?
Yeah.
Okay, good.
Perfect.
Okay,
Go
thanks a
ahead.
lot, Pascal.
12 minutes.
12 minutes. So, hello everyone. So Evolve project, it's an ICT 11 project. We have 19 partners, a budget of overall 14 million euro. The project is now reaching, I would say, the termination. So we are 6 months before the termination of the project. So it was quite a journey. Myself, I'm Jean-Thomas from DDN, and I'm the coordinator of this project. So this is the vision of an application in the early 2000s. So it's a picture from the Space Odyssey. So it's 2001. So at that time, an application was seen as a big block of monolithic logic. It's no longer the case, neither in HPC nor in the other ecosystem. So what we have nowadays, when we talk about an application, it's more like a workflow where we have different software components which are interacting between each other. So typically, we could have like a first stage where it's kind of data curation. So for example, bringing a lot of data, and then we apply some calibration or Gaussian filters or very regular logic in order to curate the data. So typically we need high bandwidth for this, so moving a lot of data. Then the next stage could be, this is just an example, but let's say that the next stage could be more deep learning or image analysis. In such a case, a GPU would be a very good fit, but we could also have a numerical simulation in the loop. Then the better match would be a CPU with double precision floating point, for instance. And then we can have analytics, we can have visualization. So the idea is that in this workflow, each stage may have a very different footprint in terms of hardware pressure. So this is bringing us to a heterogeneous platform. So since there is not a single processing device, which is the best one for all the stages of a workflow, then maybe it's better to have specialized processing unit depending on the workflow, on the workload. Then we will try to map this stage on the right processing unit. So this is a sketchy vision of the Evolve platform. So on the left, the yellow square, there are the processing unit, and on the top left, I've augmented the processing unit, the CPU, with some GPU. At the bottom left, the blue arrays, they are FPGA. So in Evolve, we have FPGA as well. And at the middle, there is processing unit, and there is also some augmented processing unit on the very left of the screen, where actually it's not additional processing power, it's a local storage. So it means that we are not accelerating the CPU, we are providing additional features to the CPU. So it's a slightly different kind of heterogeneity. So here the idea is to have a local storage, so very fast flash device within the node, so we can access to the data with very low latency. This is bringing me to the second axis of heterogeneity in the platform, is that we have also a storage heterogeneity. Some of these nodes, as I've just mentioned, they have like internal access to local storage, but there is also a fast tier based on flash device. So here we have high bandwidth, low latency, but the capacity is a bit limited because this is kind of costly device. And then we have an extra layer in the storage, which is a parallel file system based on large disk. So we have basically two axes, vertical one for the processing and horizontal one for the storage. So the machine is really heterogeneous, which means that some of the typical usage that we have a system, not usage, but typical problem are now becoming a bit more complex. For instance, resource allocation, it's no longer about allocating this number of CPU for this amount of time. We have also to discuss about the nature of the processing unit and if there is some specific data allocation also issue to address. So heterogeneity is for sure accelerating the platform, but it's bringing also a bit of complexities that we have to handle in the project. This complexity is not only about the hardware, so the infrastructure itself, but there is a lot of software work in the project. And the explanation is displayed on this slide that I've stolen from BDEC. I like it a lot, so I have to make the to cite the author, but I like this slide a lot. So what do we see here is that on the left, on the pink one, this is a big data ecosystem, software stack. And on the right side, this is HPC one, the blue one. And we see that they are kind of independent, except at the very bottom, they share the same operating system. So everything is based on Linux, but then the two software stack has evolved completely independently. So what we did in Evolve is that we wrote a bit of software, and not just a bit actually, in order to build connector and bridges between these two stacks. So for instance, now Spark in Evolve is not running on the top of HDFS, so it's not using the big data file system, but it's directly connected to the HPC IME file system. So we keep 100% portability for the application, but then we remove a lot of software layer and we connect directly to the file system. So there is a very nice acceleration here at the cost of a bit of software development for sure. So when I say we built, so there is some physical result out of it. So here you have a picture of what we have at Les Clays. So it's a Atos facility nearby Paris, and they are hosting our hardware for the project. So here you have like a CPU, GPU, FPGA, some storage as well. And this hardware is not just, a showcase. There is some real application running on it. So here, this is a very nice result that we had with an application from our partner CYBELE. So the application is dedicated to maritime surveillance. So the idea is that based on satellite images from the eastern part of Mediterranean, we can detect the vessel, so the traffic of the boat, and we can assess also if the boat are behaving as expected. And this application at the beginning of the project was 100% in production and working nicely. And 2 years and a half later, we have been able to reduce the time to result by a factor of 120. So it has been a very nice improvement based to code refactoring, a new platform, containerization, pardon me. And so at the end, we have a very modern workflow, much faster, and it's much more productive for the end user, notably because we have this nice, almost interactive display of the position of the vessel. So at the end, the customer is very happy with the result. So this application for maritime surveillance is coming from a larger basket of pilot application or use cases, which are here to validate some of the infrastructure, but each of the app has also its own scientific meaning or business meaning. We have one coming from CYBELE. It's a French startup, and it's to detect the correct growth of the crop using satellite images on the genetic growth model of the plant. We have Thales Alenia Space. They are doing also satellite observation, and they detect the changes on the ground, for instance, suburban expansion and things like that, on this use case from CYBELE for maritime surveillance. The second set of use case that we have is very important in terms of business. This is related to mobility. So here we have 4 use cases. 3 of them are mobility more at the personal level. So AVL is doing engine predictive maintenance. So based on the sensor in the engine and the model of the engine, we can detect if there is a misbehaving and predict if there is a probability of future failure. So this is very useful to basically to address the problem before it arises. So Kula is for optimize the maintenance of the car. The use case of BMW is for ride-hailing application. So it's basically, it's kind of a parallel branch and bound application. It's quite interesting. And TMA and Memex, it's a duo from Italy. So TMA is a public operator, public transportation operator. So they're operating a fleet of bus in Tuscany. And Memex is a consulting, technology consulting company, which are helping them to modernize the way that they are managing the fleet. And here the idea is to use big data to improve the service and also to react in real time to hazard that we can have in the management of the bus. So for another use case where we have good results, so for the predictive maintenance for engine, here we have from the beginning of the project up to now, we have improved the time to result by a factor of 50. So it's almost 2 orders of magnitude. It's quite nice. And it means that the application is running much faster, and also there is a gain of productivity and there is some business behind it. So it's not just about the scientific result. There is also a real economical issue, advantage out of it.
1 minute to go.
Thanks, Pascal. So at the end, what can I say? It works. So fortunately, it works because there is a very few time left now. And so it means that we are going faster. So the heterogeneous platform has delivered the expectation. So we are going faster from 1 to 2 orders of magnitude. But also, it's not only about going faster, it's also about increasing the productivity of the end user. Thanks to the containers, thanks to Kubernetes, people can manage in kind of cloud way their application and they still have very good performance. We still have open challenges. Maybe we will address them in the follow-up of this project. And at this stage, I think I have to thank you and keep a bit of time for the question.
Thank you very much. Thank you, Jean-Thomas. So we don't have questions from the public yet, but I have one question for you. What would be the evolution of converged platforms such as Evolve? I mean, you mentioned the next project.
Yes. So more at this stage of the project, so we are quite happy with what we did within the facility. So we are quite good about managing heterogeneity within the data center. But now applications tend to be distributed across multiple data centers and also to go to the edge. And here there is some, this has been overlooked at this version of the project. So we think that in a follow-up version, we should address this interoperability of the heterogeneous platform with the outside world, with multi-cloud on the edge. I think this is one of the open challenges, maybe not only for heterogeneous platform, but for data center as a whole.
Okay, we have one question from the public, from François Courteil from NVIDIA. What is the use of FPGA for those applications?
So for FPGA, we use them for basically there's a lot of satellite images. So we use FPGA in order to clean up the image. So it's really for almost signal processing.
Okay.
I'm pretty sure GPU will be good, but let's say that we've observed that FPGA are good also.
Okay. One last question. You briefly showed open source in this context. How open is this community to share and distribute these machine learning frameworks workflows?
Yes, so for the open source, what we did in the project is that we try to hook to mainstream open source projects and to push code upstream. And for instance, we try to push code within MPI. We try to push code in the Linux Foundation. So one of our partners has his code accepted by the Linux Foundation, and it's putting a lot of pressure on the code quality. So it means that you cannot do many things. You have to do a limited number of things, but extremely well if you want to be accepted in the community. That will be my answer to this open source question.
Okay. Let me check the chat. No, we have a discussion around. No, yeah. The other comments mention are not about your presentation. Okay. So, well, I think this will be, yeah.
Thanks, Pascal.
Oh, okay.
So I move to invisible mode then.
Please stop sharing.
Ah, yes.
That's important. Thank you. So, Javi, are you ready to share? Thank you very much, Jean-Thomas. Yeah.
Okay, can you hear me?
Yes, we can hear you. Hidalgo, perfect.
Good.
Thank you.
Okay, so I'm Francisco Javier Nieto from Atos, and I'm the coordinator of the Hidalgo Center of Excellence and H2020 project for HPC and Global Challenges. So,
sorry, Javi, can you please move the mic a little bit away from your mouse because we have some echo. The sound is saturated.
Now? Now?
Yeah, that's better.
Okay. Okay. So first of all, about the objectives, basically our main objective is to build the synergies between HPC-related technologies, including HPDA and also artificial intelligence, and the global challenges. So the point here will be, what is a global challenge for us? And this is problems that may be happening in some localized areas, but that this is replicated in many places in the world, or problems that are cross-border. I mean, they are affecting many countries. Okay, I will give you some examples later with the list of pilots that we have. So what we are doing in the project is basically to improve the way in which we do simulations with the HPC tools in this Europa Challenges domain. In most of the cases, we are doing this with AM-based simulations. So this is one of the main things that we are addressing, just to improve the parallelization of this kind of tools. Of course, we are also using high-performance data analytics and artificial intelligence, and this is integrated in the workflows that we have for the simulations. And another important aspect in the project is the coupled simulations. So we have simulations which are very complex, and in some cases they require the outcomes from other simulations, such as, for example, weather forecasts. That could be useful, for example, in case of migration, pollution, things like this. Okay. Another important objective that we have as a center of excellence in HPC is just to connect different communities. So people from Global Challenges and people from HPC need to collaborate, and also the part of training. So this is actually one of the services that we provide training in different areas. We have a specific training for the HPC tools, a specific training for the Global Challenge applications, and in some cases also both of them. And then the last point to highlight here is that we are building a portal that and the idea is to have it as a kind of single entry point, like a one-stop shop. So our stakeholders will be able to access to all the functionalities and all the things that we provide through this portal that contains a data catalog, a solution for running the workflows in a very easy way, so you can run your simulation with just a few inputs. We also have tools for user support, like questions and answers and ticketing systems. We have also Jupyter notebooks, so you can play around with your codes and things like this. So the idea in the end is just to facilitate the stakeholders to use all our tools and to engage their participation. About the kind of pilots that we're addressing, first of all, migration. So we have a case in which we simulate refugee streams according to different conflicts, and the idea with this is to investigate what happens when some policies are applied. So for example, there's a conflict in a country, and then one country which is next to it is closing its borders. So what's going on with the people, where we should move the support, and all these kind of things. Another case is Twitter messaging simulation. So basically, just to analyze what's going on in social networks. We analyze the structure, we simulate, we recreate the structure of the social network, and then we simulate the messages being published and retweeted and all these things in order to understand how they may work in cases like fake news or marketing campaigns, so you know how you could deal with them. Another case, much more localized, would be urban air pollution. So basically, we are simulating how the pollution is accumulated in some parts of the city. And the idea is to provide the stakeholders some tool in which they could just test what will happen if they apply different policies. So for example, minimizing the traffic, or just avoiding the traffic in some parts of the city. And finally, we include one new use case, which is about COVID-19 simulation. So basically, we simulate how the disease is spread in city or in neighbor, so we can understand numbers about the people infected, how much people need to go to the hospital, and these kind of things. And also, it's possible to apply different policies. So, okay, what happens if we apply a curfew, or if we are just closing some concrete places in the city and things like this. So in order to do this, we have several main codes. I just wanted to bring a couple of examples here that have a quite good scalability, and they're improving. One would be FLEE. FLEE is the solution that we use for the migration simulation, which is an agent-based tool that is simulating the movement of people in different areas. So basically, you can forecast where people will be moving, and actually we use what we call the location graphs in order to understand which routes they will follow. Okay, right now we are doing simulations up to 1 billion agents, and we can use up to more than 16,000 cores per each single run. And the point is that when you want to do this kind of simulation, you have to do many runs. So we apply ensemble runs, which means that we can reach a very good scalability. Of course, this can be improved. So we have ideas under development right now, like improving the rule sets that we have, do this coupling with weather forecasts, as I was mentioning before, include more agents in the in all these things like goods which are moving in the area and things like this. Another good example is the one for social networks, which is HIST. This is the software that we are using for doing the reconstruction of the social network. So basically, you simulate how the networks are structured and how people are connected. This is done with graphs, and we have already developed a tool as well for simulating the probability of interaction between the different people and messages. This is, I mean, we have been doing simulations with about 1 million nodes in the graph, and we are able to use more than 32,000 cores per each run. And also in this case, you need to do ensemble runs because you need to, I mean, it's not very deterministic kind of simulation, so you need to run several times in order to understand what's going on. Of course, I mean, we also have many things to improve, such as, for example, this parallelization of retweets feature, simulate larger communities, because 1 million nodes representing 1 million Twitter accounts is good, but you may have, I don't know, if you want to analyze what's going on with the COVID-19 messages, you will have lots of million of nodes, lots of million of people talking about that in Twitter. Challenges towards Exascale. So the areas in which we are investing more time in our research are basically the part of benchmarking, identification of bottlenecks in the different tools that we have, with a specific focus on sometimes in the input and output operations, because sometimes we need to store a lot of information of what's going on with the agents. Also, we do benchmarks using new architectures and even accelerators sometimes. This is something we are doing, for example, for the urban pollution, the application of GPUs. We are interested in supporting the EPI in the sense that we would like to be able to do some small port of small codes in order to see how it works, how it behaves. Taking into account that this will be one of the processors to be used in the future. And of course, we work more in the scale up of the models for bigger simulations. So we have different ideas for all the cases that we have. So at some point, it would be meaningful to reach some exascale. Another point is the workflows in which we are combining HPC tasks with HPDA. So as I mentioned before, we are doing a lot of ensemble runs. And in the end, what you need to do is to take a look at the results of the different simulations, apply some HPDA techniques in order to extract the information that you may need. So you ask questions to all the data, and then you see what worked better or what didn't work. For example, in terms of urban pollution or COVID-19. So you have tried the simulations with the application of different policies, so you could extract information about which ones worked better. And then we have the part of the coupled simulations. So we consider two different ways to do it. The weak one, which would be just like a REST-based coupling, or even with files, and the other one, which would be a strong coupling, which would require the exchange of messages between the different simulations. And we are working right now in the coupling with live data, in the sense that we have for the urban air pollution a setting which we deployed sensor networks, and then we want to take this information in real time and to use it for the validation of the simulations. We have like quite good of list of services from the Center of Excellence of things that we offer to external people, such as the consultancy, just for providing solutions in different areas. Of course, we have training. This is actually something that we have already done with, for example, with the National Competence Center in Sweden. We prepared together with them a training for HPDA. We provide user support with respect to the different tools that we have, and also to the applications, co-design related to these benchmarking activities. We have repositories with data, with code that can be used, and finally we have this portal that is the one-stop shop. Finally, this is my last slide about success stories. I just wanted to highlight a couple of them just to show how we are working with external entities. In the case of migration, we have been working with people from Save the Children. So we have been doing simulations about the migration part in order to see the people flows and where they were going to arrive. And once we estimate the amount of people that is going to arrive to some place at the concrete time, then it's possible to provide support there. And another one is the COVID-19. So we have been collaborating with the National Health Service there in UK, and we have done several simulations in a couple of neighbors in London, where we apply this SAIR concept, success activity response information recovered models, in order to implement this simulation I was mentioning before. And I just want to encourage all of you to become an associate partner. Just you can collaborate with us, just doing or preparing with us simulations for concrete people you may know. For example, in our case, we are preparing now simulations for COVID-19 for the region of Madrid with one of their hospitals. In other cases, we are preparing vulnerability simulations from different cities. So there are many things that we could do together, and I invite you to collaborate with us. And that's all. So you have some questions?
Thank you. You're right on time. Actually, we have one question from the audience, from Kemal Delik, which is, how do simulations agree with real-world situations? Actually, he has an idea about the answer because he gave us his own proverb after saying all simulations are wrong, but some are useful.
Okay. Now, for all the cases, we have a validation activity, right? So in many times what we do, for example, let's look at the migration one, right? So there is some public information about the conflicts that happened the previous years. So what we do is you do the simulation with the initial data, let's say, and when you obtain, you simulate, for example, 1 year or several months, and then you compare the information that you get from the simulation with information that it's available. This was information available for the United Nations, UNHC, I think it was the name of this entity from the United Nations, in which they have deeper information about the Syrian conflict, for example, or several conflicts in Africa. So they have historical information, and we are doing that. In the case, for example, of urban air pollution, we do the simulations, and then you can compare that with the sensors that are deployed in the city. In this case, we are very focused on the city of Győr, which is in Hungary. There is the place where we deployed a sensor network. So we have sensors there in the field, and we can compare directly with information that we are collecting. In other cases, we will depend on the information from another city. So we have, for example, a model for Stuttgart, and in that case, we would depend on the information provided by Stuttgart in order to do that.
Thank you. We have still some time for one question, maybe, so I'll ask mine. How do you expect to scale up your models, and are there reasons to do so?
Okay. So this is actually something that has been discussed several times. It makes sense. For example, in the case of migration, right now we are simulating concrete conflicts in an isolated way. So you may be simulating what's going on in the Syrian conflict, but then you also have other conflicts in the area. So yes, simulating several conflicts at the same time in that area of the world, it would take a lot of resources and would require actually some communication, some coupling between the different simulations as well. In other cases, let's take, for example, the social networks. As I was mentioning before, if you take or you want to do some case in which you want to analyze what happened about messages, marketing campaigns with a rock band, let's say, you will have lots of millions of users which are interested in that and will be publishing things. So you can simulate very, very big networks. And this is also applicable, as I mentioned before, to COVID-19 and other cases. In other cases like the urban air pollution, the way to scale up right now is more related to the resolution. So it seems that there will be, or there are already, some regulations in which cities will need to have very good resolution about what's going on with the pollution. So the idea is just to have just a few square meters of resolution of the problem that requires lots of millions of cells when you're simulating a city.
Thank you. Thank you very much, Javi. So, well, it's time to hand over to the next speaker. So thank you very much.
Thank you. So
Can
I
you
stop sharing.
please stop sharing? Yes. And while our next speaker, Jost, is getting ready, I would like to remind our audience that the projects presenting today are exhibitors at the Teratec Forum. So if you want more information, please visit their virtual booth. Thank you very much. Jost, are you ready?
Yes, I'm ready. Can you hear me?
We can hear you. We can see your slide.
Perfect. So good afternoon or good morning, everybody. I would like to present PRACE and HPC Gig and how they support the communities on the road to Exascale. And I will focus on one aspect that is maybe somewhat less known because it's relatively new within PRACE, software efforts towards forward-looking software. So my name is Jost van der Wondelen. I work at the Swiss National Supercomputer Center, which is part of the ETH in Zurich. Now, many people might know PRACE already. It's basically a large partnership between currently 26 members that provides access to resources to perform simulations on large infrastructure. And it's large in the number of projects enabled. It's nearly 1,000 projects, and more than 30 billion core hours have been awarded since PRACE started, so about 10 years ago. It's predominantly giving access to academia, but also about 100 projects or so were companies that have been supported. PRACE has also a training aspect with roughly 20,000 people that have been trained on the use of HPC resources. The next slide gives a quick graphical overview of the machines, the tier zeros, the largest systems that are part of the PRACE project, to which, of course, people can get access with a competitive scheme that selects projects for excellence. All these machines are fairly large installations in Europe. Now, PRACE is also part of HPC Gig, and that's a high-performance computing governance intelligence gathering group that has as a goal to support the efficient and sound operation of the HPC governance. For example, support the Euro-HPC joint undertaking to gather the information needed to make decisions, and for example supports the Euro-HPC advisory groups, the INFRAG and the REAC. PRACE is part of this ecosystem and also has been promoting or making clear that there is a need to develop software and tools to enter this exascale era. All the hardware is, of course, extremely important, but software acts as a multiplier for the invest in the hardware. And with this in mind, PRACE has several actions to support the software development in their project. There is one aspect which is well established, giving users support and help to enhance their codes once they have received a grant or given help in benchmarking their codes. But recently, about 2 years ago, PRACE, as part of 6IP, started to fund explicitly projects to develop software with the exascale or the pre-exascale in mind. And that's this initiative I would like to go a bit more in detail today. It's called Forward-Looking Software Solutions, and like any European project, this is in a work package. Work package 8 is what we use for that. And we have three main goals. That is to deliver software solutions in the form of high quality and transversal software. So high quality, open source quality was mentioned. That's what we aim for. And transversal is not necessarily limited or linked to one particular simulation package, but reusable between packages. And with this development, clearly aim at the top tier pre-exascale systems in Europe. These are projects that are strategic in mind. So the partners have been asked to match the investments with significant in-kind funding. And all of these projects are long-term. So we give 2 or 3 years to basically develop software that is deemed important with significant effort. And we do that with the idea that we have to allow for disruptive approaches. It's not just porting, it's really giving people the opportunity to modernize HPC software and to leverage software technologies that are adopted and developed and maintained by the big players in IT. This was started as a competitive call. 10 projects were funded. Each of them involve 2 to 5 partners. The partners there are HPC centers in Europe or associated members to PRACE. I will go a bit more in detail of the projects, but all of these projects have software engineering keywords associated that I just listed to give a quick overview. So a lot of emphasis is on API design and code reuse that's needed for this transversal aspect. We pay attention to the scalability of the codes, and of course, if you want to be ready for the pre-exascale systems, to GPU acceleration in a performance portable way. We know there will be multiple vendors of GPUs in the pre-exascale systems. We address, I would say, modern or contemporary topics. For example, as a project that touches on quantum computing, how can we support that with traditional computing? How can we get ready for the post-exascale systems of the future? And also people that explore more modern programming environments. It's not just Fortran anymore in HPC. People are using things like Julia and more modern techniques like task-based programming or futures in these things. So it's really about moving legacy forward. These are all projects that have open source codes, so public repositories, issue trackings, and so on GitHub. Open meetings where these results are being shared with the stakeholders, and that's important. This is not an isolated effort, but these projects have, for example, letters of support of COEs or large user communities. And really the goal is to upstream developments and make it available for the users of the infrastructure. In the end, this makes the infrastructure significantly more efficient, and that's the goal of this project. There are 10 projects, and of course I cannot cover them all in the remaining few minutes of this talk. What is important to highlight is, and this is not the yellow part, these are the projects I will discuss, but to highlight conceptually is that this is not a single domain or just a domain supported by the COE. It's rather broad. So, for example, plasma physics is a domain that is important from the usage point, but for example has no associated domain. It's actually represented with 3 projects here. And also projects that are not really domain specific. For example, programming techniques that are based on task-based programming and basically develop the runtime support for these programming techniques, or develop more generic reusable components. For example, having performance portable linear algebra in dense or in sparse forms. I will talk about 4 projects. One is on biophysics simulations. One is generic Halo exchange, how you can exchange data and make your calls to scale. I will briefly touch on the quantum circuit simulation project, and then a project where people use finite element methods, which is very important for small and medium enterprise and industrial applications. Now, the first project named NBLib is the idea there is that we have really well-established biomolecular codes and GROMAX is one of the examples there, and it's the partner in this project as part of the BioExcel COE. And these engines are very efficient, but the framework is relatively rigid, or it's difficult to reuse the code in different applications. So if you come up with a new concept, a new idea, how can I, for example, study some properties of a system in a new environment, free energy properties, rewriting the code was very difficult, and this project basically implemented APIs and made a user-friendly interface to the internals of this efficient code so that users can much more easily make problem with their models and develop codes that are then useful. This was successful in that all this work has already been upstreamed and is part of the GROMAX release that has been made earlier this year. The project itself runs till October, so there's still some work ongoing to extend this API to larger parts. Now, GX is a library, and that's very interesting. It targets a really important primitive in parallel computing, namely halo exchange, the exchange of data between nodes in a parallel computer. And this is in a generic way. So initially conceived for the weather and climate domain, as part of this project, we had a partner in astrophysics, and basically this was made such that this concept, this primitive, can be used in multiple different codes. It's also very interesting in its design, in that it is clearly separating the user side from the library, the capabilities that are being generated by this library, and from the hardware capabilities. So this is one of these HPC codes that goes clearly beyond NPI and adopts lower level libraries and frameworks like UCX or libfabric, or certain techniques in on-node communication to reach the highest possible performance that is difficult to reach with NPI, despite its long tradition in the HPC sector. It has, for example, difficulties to deal with highly threaded code, and these lower transport layers can deal with this much better. This project has been successful in integrating in a weather code and this astrophysics code, and also has been used as part of the procurement benchmarking. So one of the pre-Exascale systems actually used this project to get whatever is best on the market when it comes to communication. Quantex is a project that simulates quantum circuits, and it's of course the basic building blocks of any program that runs on a quantum computer. And you could wonder, why do you want to simulate that on a traditional machine if quantum computers are there to revolutionize and basically do calculations much faster? Well, it's clear that writing quantum programs on the quantum computer is really not so easy. And to be able to write efficient programs, to understand them well, to debug these programs, we need tools. And simulators running on traditional hardware are definitely going to be part of the programming environment for quantum computers. And in this project, tries to implement something that is called as tensor networks and use that for factorization of these quantum circuits. This is interesting, I said. It's a very modern development environment based on Julia, containerization, lots of things we know from the machine learning fields, and has from the beginning on been designed to target heterogeneous architecture. So accelerator support has been designed in. And then finally, I would like to touch on this last project. This is a project that deals with finite element codes. And of course, they have important use cases in engineering and in small, medium enterprise applications. And this project, I would say, has two goals. First of all, is moving this code forward towards heterogeneous architectures. It's well known to scale to up to 100,000 cores. It is also now being moved to modern accelerators like the A100 and so on. Now, as I said, it's an important code for industrial applications, and to make it more easy to access HPC resources, they are also working on a platform where they want to provide this capability as a service. They call it Solver as a service, and they have basically an interface that makes it quite easy to have a complete workflow running using this Espresso code on HPC resources. With this, I would like to thank you for your attention.
Thank you, Joost. First, before we get to your questions, I would like to check if Sophie is back with us and will be able to finish her presentations after the questions, of course. Sophie, if you're here, please make yourself visible. Okay.
Yes, I'm back.
Excellent.
I
So
have a
while you get ready, we'll answer your question, okay? And we lost you on slide seven, Sophie.
Okay, thank you.
Okay, so Joost, back to Joost. We don't have any questions from the audience as far as I can see, but of course I have a question for you. There are many actors in the European HPC ecosystem that develop software. I mean, for example, COEs or academics, obviously. So what differentiates the work done in PRACE?
Okay, so Pascal, thank you for this question. I think that's a question that could be part of a long discussion. I would think that there are clearly different points of view that these partners can bring in. So we collaborate, obviously, as as PRACE as an institution. We collaborate with COEs, provide resources, and we hope that they provide software that runs on the systems. But I would say, for example, COEs have a domain science point of view, while PRACE and the HPC centers that build PRACE have the software engineering point of view, and kind of together they can become stronger if we both play with our strengths. I think that's the way I see it. And then the other aspect that centers have is that they have usually this kind of special relationship with vendors. We have early access to information that might be NDA, and so it's easier with this vision to plan ahead, to make strategic decisions in the design of software and development direction based on what we know will be the architectures of the future. And I think that's something that plays to the strength of these kind of developments. And I would say the final aspect is that the kind of people that work at, for example, in the academic landscape, their goal should really be to excel at science and, to publish, have new ideas, new models, while often the goal of people working at an HPC company or so is to deliver software and quality services. And I think that's also nice. People in PRACE often focus on the software engineering aspects, and I think that's complementary there.
Okay. We have a question from the audience. What about the other projects, those related to linear algebra solvers?
Mm-hmm. So
can you say a word? We have just a couple of minutes.
Sure, I can talk a little bit about this. So one of these projects has as a goal to create a performance portable linear algebra solver, in particular an eigensolver. So depending on your background, you might know that this is a key capability for a lot of fields, in particular material science and quantum fields, where they need eigensolvers. And the idea is to redesign from scratch a distributed and performance portable eigensolver using a future approach, so task-based programming and various backends that target AMD and NVIDIA GPUs as well as CPUs. And then there's a second linear algebra project that has a background in quantum chromodynamics, if I understand correctly, where they use sparse linear algebra, basically Krylov solvers, to address problems that are much larger, but of course have a sparse data structure.
Thank you. Thank you very much. I can't see any other questions. So thank you, Joost, for this interesting presentation. Actually, I'd never heard about those PRACE projects, so that was really interesting. So, Sophie, are you ready?
Yes.
Yeah, can you share?
Yes, I hope
your
the
screen?
primary connection will hold up.
Yeah, and I hope they will let us finish. I hope we won't be cut at past.
So can
Yes, yes.
Okay, so
Go ahead.
I will
Thank you.
dig a little bit more in detail on the subcase one. So what Atos did is some data cleaning. and to use some deep learning technologies like PRED or plus to use the satellite data to get the sea temperature and to predict the sea temperature for the following days, and then to use some gradient boosting algorithm to predict, based on the information of the temperature, the other species of fish that can be present and the vessel's horsepower and fishing métier, the quantity of fish that will be caught. And so a little bit about the CYBELE architecture platform. So it's a service. CYBELE users, as I mentioned previously, can have very diverse it can be a data scientist that will build a model, or it can be a farmer or fisherman that will just access some dashboard and data and information available to him. And for that, everything of the HPC and the big data is kind of hidden. It's managed by Kubernetes and some Slurm and Torque modules. So thank you. Sorry for the interruptions. And if you have any questions.
Let me check if we have questions from the audience. Not yet, but I have a question. I mean, your project is focused on agriculture, of course, but can the work done in CYBELE and specifically the platform you were just showing, can it be used for other domains?
So yes, it can. As you can see, it's pretty data and topic agnostic. So it can handle a very diverse type of data, pictures, time series, from sensor, pretty much apply to whatever domain you can think of.
Okay, and thank you. And we have a question from the public, from François Courtet, NVIDIA. How do you use jointly Slurm and K8? I hope you know what he means, because I don't, but then that's not my job.
So I don't. I'm a data scientist and I have basically no knowledge in hardware. That's why I really like the CYBELE. Everything is hidden and is easy for me to use. But if you can send me
Maybe
his
we can
email.
get back later to François.
Yes.
Okay.
Yeah.
Good. Any other questions to Sophie or to the other speakers? No? Well, then we will put an end to this session. I was delighted to moderate again this project session. I would like to thank our speakers today, and I would like to thank our audience. We had many interesting questions today, and I'm glad you were able to discover those projects, because sometimes little is known about what they do, and they do lots of interesting things in very different domains. And today we had really a good overview. So I will really finish by encouraging you to visit the booths of those projects. This is a way to get in touch with them as well. And that's it. So I hope you enjoyed this, and thank you, and bye-bye.
Bye.
Anything to add, speakers? Dear speakers? No?
Thank you, Pascal.
Okay.
Thank you, Pascal, for the outstanding job.
Oh. Thank you very much.
Thank
Bye.
you. Bye.
Bye-bye. Bye-bye.